This video is going to be dealing with TinkerCad and voltage regulators. So we're going to basically zoom in on the 5 volt voltage regulator, but TinkerCad also has a 3.3 volt regulator, so you can play with that. Electronics that basically are coming up are more 3.3, and that's just because of the lithium batteries are it's more workable at that voltage. We've basically got the ground, we've got an output and an input. This one's in a different order. We have input and we have ground and then we have output. So we're going to start off by looking at a diagram that I got off of the internet very quickly. And so we have our 9 volt battery on this side. So 9 volts is fairly useful for some things, but typically 5 volts is what we typically have in electronics. And now we're moving to a 3.3. So this item right here is a voltage regulator. It's got the input. You can sort of see that the positive side of the battery is connected to the input. There is a larger capacitor. So in this case, it's a 3.3 microfarad capacitor, and it's not showing polarity, but often you would have a symbol indicating that's positive or negative, and I'll show you that more when we get to the actual physical components. The grounds are all tied together, and even when you look at this LED, which we'll have in one of the circuits, that's going to be tied to ground on the negative side. You'll notice that this right here indicates the ground of the LED. We have a resistor. In this example, we have a 1K resistor, but we're going to play with different values. And then this is a smaller capacitor. And this is the output. Okay, so we can put that away and we can start looking at the same situation. I'm going to hit simulate. You can see that the voltage being fed is a 9 volt battery, and that we've just have a multimeter set for volts. And we've got basically the package or the integrated circuit. If you were to basically remove the epoxy, you could sort of see some of the circuits in that, but very often we're looking at essentially a black box with a couple pins coming out. Often the top of it is linked to ground, and you can use that to dissipate heat if you wanted to. Sometimes you can get a little heat sink to screw onto that, and other times it mounts to the board that you'd be working with. On this side is the larger capacitor, and you can see this stripe right here indicates the ground side, so that's going to be set to the ground pin. And the other side is going to be the input voltage. So you can kind of think of this as a little battery that's going to fill in any spikes. So if we have a massive drawdown on one side, then this is going to help feed that faster than the battery can handle. And on this side, we've got the smaller capacitor, and that's for filtering out smaller bumps, rises and falls in the voltage itself. So you can sort of see what's going on. You can tell that I'm hiding my wires. I'd have to shut the simulation off just to make things look neater, and they're still there. So when you're making yours, you can do the same just to make a tighter or neater diagram. Anyway, so that's one example, and then I have another one here on a breadboard. Breadboards are just they're easy to work with, because if you were to do this, you'd have to solder the connections. And in this one, it's all temporary connections. And when I hit simulate, you can sort of see that we've got 9 volts. And if all these pin holes are connected, so typically we use like a 20 or 22 gauge wire that's solid, and we use that to make the connection. So these are all connected. These are all connected, so that's the positive and negative bus, I guess. And then these pins are connected. Now I have a little magic trick here. I needed more than just one row to show you, and so I'll see if I can move this component out of the way. So you can see that I've joined these wires together so that these pins F through J are also connected to A through E, and that's just a little bit of cheat to get more pins. So I could jam them all in onto one half of the mother or the breadboard, but in this case I just wanted to have everything set apart so that it'd be easier to understand. So the black wires are going to ground just as we were before, and that's from both sides. And these wires here, so this is going from ground, so all the grounds are actually tied together from the battery all the way to the top rail and even to the LED. Okay, and then the input, this is 9 volts if you're to measure it, and it's tied to this, and that's why this shows 9 volts when I simulate it. Put that back on, and it's not exactly 9 because this is drawing it down a bit. And so we've got basically the positive and negative, and then this is the output side, and it's going to this other rail to feed 5 volts. And this is just a little capacitor to even it out. So you could actually remove both the capacitors, and I think the circuit would still work. Let's see if it does. Yeah, so it still works. It's good practice to have them there. It smooths out the voltage, and later on, if we're looking at an oscilloscope, you'll understand why. Okay, so I think that's it. I'll bring back the diagram, maybe help you. Is that just we have power in on the left and power out on the right, and we have the capacitors to smooth out the any dips in voltage. And one of the things that I added, I guess I didn't mention this, is that if you click on these resistors, you get the value. So 220 is 220 ohms, and this is also the same. And when we run the simulation, because this is 9 volts, we're getting a warning here, but because this is 5 volts, we're not getting a warning, even though it's the same setup. Okay, so hopefully that makes sense. Good luck, have fun duplicating this in your example.